3, Lesson 14, Proving the Pythagorean Theorem. Exercise 14.1, Notice and Wonder, Variable Version. So what do you notice? What do you wonder? Go ahead and pause the video and try to think of what you notice and what do you wonder. Okay, so hopefully you pause the video. I realize that if you take the length of x and you combine it with the length of y, you end up getting c, right? That entire hypotenuse, right, for this right triangle. Oh, it's a right triangle, right? So I realize that. There's a 90-degree segment here, which we called the altitude, right? And that was from lesson 13, right? We talked about that. Because of the altitude being created or inscribed in that triangle, that right triangle, we have three similar triangles. All right, that's good to know. They definitely talk about Pythagorean theorem, so I'm thinking like a squared plus b squared equals c squared, right? So that might be more relevant to what's happening now. Okay, if you notice anything else, let me know. Exercise 14.2, prove Pythagoras right. So we have these two kids, Elena and Diego. Okay, Elena is playing with equivalent ratios she wrote in the warm-up. Looks like she created a proportionality statement here. And then, so a is to x as is c is to a. And then she ends up getting a squared equals x times c from that. Okay. Diego says he got b squared equals y times c. And then he says the a squared and b squared, right, from here and here, remind him of the Pythagorean theorem. Okay. Elena basically says, well, the Pythagorean theorem is a squared plus b squared equals c squared. And she bets that we could figure out how to show that. So first things first, how did Elena get from her proportionality statement to over here? What do you think? Okay, so hopefully you realized she just cross multiplied, right? You have a divided by x equaling c divided by a. If you go ahead and cross multiply, and I know some of you also have done that in the past, which is fine. A times a is a squared. X times c is xc, right? So she definitely cross multiplied. Okay. What equivalent ratios of side lengths did Diego use to get b squared? All right, so this is number one. Number two, I'll do over here. Okay, so how did Diego get b squared equals yc? Okay, what ratio did, or what proportionality statement did Diego end up using? Well, he definitely had to have b going to y, and then c is to b, right? Because b times b is b squared, y times c is yc. So he had to have that proportionality statement going from, okay? So Diego was definitely operating, b is to, so let me highlight what Diego was looking at. B, right, is to y. So he was comparing the medium-sized triangle, okay, to c. So this is, so just to clarify, b is, because this is a nice review for lesson 13 with proportionalities. So b, right, is the hypotenuse for the medium triangle, and y is the looks like the base. Yeah, the base is the medium, the middle longest side of the triangle. And he's doing the same thing, except this time it's with the other triangle, right? C, which is the hypotenuse for the large triangle, to B, which is the base of that triangle. So he's definitely keeping up with hypotenuse to the base. All right, so that's a good reminder of what these kids are doing here with their proportionality statements. Okay, so number 3, I kind of overkilled number 2, but I think it was a good reminder of how these kids are getting these statements. Number 3, prove that a squared plus b squared equals c squared in a right triangle with legs A and B and hypotenuse length C. Okay, so let's see. We know that this right triangle, right, gets an altitude that basically creates 3 similar triangles. These kids create these proportionality statements. They create AX is to CA, and they create B is to Y, as is C is to B. Right, so they create these two proportionality statements. They could create a third proportionality statement using a different combination of triangles, but since we already have the a squared plus b squared, we're just going to focus on that right now. So let's see, they said a squared equals x times c, right? That's what Elena said. And Diego said b squared equals y times c. So if you add a squared plus b squared, what you really get is xc plus yc. All right. And I notice that both these terms have a c in common. So I'm going to factor out that c. Okay. See how I factored out the c? Do you see? All right. Now what? Okay, we know that x plus y is what? Wait a minute. X plus y equals what? Flashback time. X plus y was c. So if x plus y is c, this is just technically c times c, which is c squared. Bum, bum, bum. Therefore, a squared plus b squared equals c squared. Okay? These two kids were onto something, for sure. All right. 14.3. An alternate approach. So when Pythagoras proved his theorem, he used 2 images shown here. Can you figure out how he used the diagrams to prove that a squared plus b squared equals c squared in right triangle and hypotenuse length c? Okay, let's look at the pretty pictures, because this is a very visual thing. Let's see. I notice we have b squared here, right? If you think about area, right? Because you have to remember a common application of this kind of algebra is very involved with area, right? So we have b squared giving us that 1 square. And notice this length here is a, so this is a, that's a, so this is a squared. And then we have 1 triangle, 2 triangles, 3 triangles, 4 triangles. Okay, you guys notice that? So let's look at the other image. We have a triangle, a triangle, a triangle, a triangle. And then we have, I'm going to go ahead and call it c squared. All right, because we have a, b, and these are c's, right? Like if we remember the right triangle situation. And yes, I'm assuming that these are right triangles because we're using Pythagorean. All right, here. So whenever I think of Pythagorean, it's like definitely a right triangle should pop up in my head, right, in long-term memory. Okay. Are these two images uh, the same size? They look like they're the same size for squares, right? They just carved them up in different ways. So we do have four triangles, right, on the left square, plus the uh, green triangle, the a squared, plus the b squared, which is the uh, here. Let me highlight it. Right, so b squared, right, is that triangle right here. Uh, let's see, a squared is that green triangle right here, and those four triangles come from these four triangles right there, right? Okay, and they should be equal to the other square, right, which is carved up in a different way. It's carved up by four triangles, right? One here, one there, one there. And we have one of those blue squares, right? Very nice. Um, what do both the left-hand side and right-hand side have in common? They both have 4t, right? So you use the subtraction property right there. What do you notice? What's left? So this is actually one of the proofs that you can use to find that a squared plus b squared equals c squared. It's a nice visual proof for certain. Okay. In summary, in any right triangle with legs A and B and a hypotenuse C, we know Pythagorean theorem: a squared plus b squared equals c squared. All right, but why does it work? We can use an altitude again right here. Right, it has to have that 90-degree uh, intersection. So we have an altitude. Draw the hypotenuse of a right triangle to prove the Pythagorean theorem. Looks like they changed the letters, right? I think that was X and this was Y, but they changed it to D and E. It's fine. It's fine. Still works. But remember, when we have an altitude that carves up a triangle, a right triangle like this, we then create, all right, by angle, triangle, similarity theorem, three triangles that are similar. So from this, we get three similar triangles. Okay, and they're all still right triangles in this process. And from those three triangles, we can create proportionality statements that give us this. This is the part where Elena and Diego are talking about a squared and b squared. And hey, does that have anything to do with Pythagorean theorem? I think we use x plus y in this situation, which became c. So this is really just c times c, which gives us c squared, right? All right, so using Pythagorean theorem, we can describe a triangle's angles without ever drawing it. For example, a triangle with sides 8, 15, 17 is right because 17 squared has to equal 8 squared plus 15 squared. All right. If it's if a triangle with the side lengths 8, 15, and 18 is obtuse because 18 squared is greater. Okay, so obtuse if it's greater, and if your side length is less than the other two being squared, then it's acute. So we can actually differentiate just by using Pythagorean theorem. All right, we could tell right away, like, hey, if you take those two sides and you square them, it better equal the other one squared. If not, it's not a right triangle. All right, and if it's greater than the other two sides being squared, then it's obtuse. If it's less than, it's acute. All right, that's it. Have a beautiful day.